All right. I passed out the labs. I'm going to do a quick rehash here. Passed out the labs. The first thing we did was somebody determined what the atmospheric pressure was right now in Bessemer, Alabama, and we came up with 31.1 inches of mercury. We did a conversion of that, first from inches to centimeters, using 2.54 centimeters as 1 inch, then 10 millimeters per centimeter, and came up with 764.54 millimeters of mercury. Okay? On our data sheets then, on the table on page 152, under barometric pressure, we put both 30.1 inches of mercury and 764.54 millimeters of mercury. That's under barometric pressure. And on the top of that page, we changed the trial 1 and trial 2 to thermometer 1 and thermometer 2. Okay? So those are our barometric pressures. Okay? Deviation from normal was 760 millimeters of mercury. So the difference is positive 4.54 millimeters of mercury. So that's our deviation on the line below that, plus 4.54 millimeters of mercury. Okay, next thing I did was give 2 thermometers to each team, teams of 3, and they get to know their thermometers. One of them is thermometer 1 and one is thermometer 2. Okay? Now you take and what you need to do is distinguish your thermometers from any others, and I have it written somewhere there. The 4s came out really lousy, so that chicken scratch at the top, that's your 4 there. Most of the rest of them I think are fairly easy. Number 1, one of the number 1s is hard to read, but just know which is yours. Okay? And if you will come with your 2 thermometers, place them in the water that's here on the heater. Okay? And soon we hope that that water is going to be boiling. It's very close now. You can see little bubbles coming up, but it's not quite boiling yet. So go on and put your 2 thermometers in and be able to tell your thermometers from everybody else. So everybody come put your thermometers in. Okay? A couple reasons is putting the thermometers in is going to drop the temperature a little bit, so I want to get it back to boiling as soon as possible. So know your 2 thermometers and which are yours and which is 1 and which is 2. So all 5 teams put your thermometers in. Okay, I got 3 out of 5.
Don't mess it up, Will.
4 out of 5. And 5 out of 5. What we're going to do is wait just a few minutes until it actually starts boiling. Okay? Now, what I'm going to do while we're waiting for that is get... Okay. Now, does someone... All right. Just going to take a few minutes here. Let's see what else we can do while we're waiting. Oh, I know one thing you're going to do. I forgot to bring up rulers. Let me run down and get rulers. I'll be right back.
Like this morning, I had ice and orange juice. It's full and get old. Water, tell her down there. Well, you have tried first birthday. Flawless. Oh, you just continue to talk. Shows what. Centimeters on bottom. Centimeter on top. Yeah, that's that. How do you pronounce that? Where's that? Huh? What category is that? Huh? I can't believe you went down there. Stove. Says it on the wall. Yeah. As soon as you walk in. Never put this on my
Okay. All right, we're boiling nicely now. Okay. So what I want you to do is each team come up. Now, listen up, folks. Okay. When you're measuring the temperature here, probably not best to have it on the glass. So I'm going to pick up one of these, and this happens to be a number 5. I'm going to hold it off the glass, but near the bottom, near the center, and read the temperature there in degrees Celsius, the nearest degree that you can. Okay, I'm putting that right back down where it was before. So every team come up and measure temperature, thermometer 1 and thermometer 2, what the temperature is at boiling. Okay?
Is that the water yellow?
Okay, thermometer 1 and thermometer 2. And once you've read it, both thermometers, you can pick them up and get them out of the water. I already sat down again. Okay. Okay, don't get it all the way out of the water, just off the bottom of the glass. Huh? Once you've read the temperature while it's in the water, record it, read, record, and then pull them out. Thermometer 1 and thermometer 2. Okay? And what you can do then is take it right over there to the ice, hey, whoa, 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 and stick it in the ice. Okay, once you've read it, be sure you read it. Okay? Read your 2 thermometers. Thermometer 1 and thermometer 2. Oh, you know where to put those on data table 1. Observe. Okay, wait, sorry. I got it backwards. We're doing observe boiling point. We should have started with melting point, but that's okay. Be sure you put this in the third thing. Thermometer 1, observe boiling point. Thermometer 2, observe boiling point.
And then, right in the ice?
What's that? And then put them right in the ice. They should sink down pretty nicely. Okay? So all the teams read your thermometers and getting them out. Sorry, I wasn't paying attention. I put them in boiling point first, and we really should have done melting point. Not that it matters. Okay. Remember, when you're reading it, get it off the glass, but still in the water, and read your temperature. Okay. What's that? Yeah, go ahead and put them in the ice.
Is that melting point?
What's that?
Is that melting point?
Melting point. Okay, now another thing to notice is, we should have done the melting point first, but I wasn't paying attention. So I'm going to turn this down a little bit. But while you have it in there, is the ice still melting? Now let it get to equilibrium, and once it does stop, does the temperature change as the ice is melting? It does. Now, not as your thermometer is cooling, but as the ice is melting. Leave it in there long enough, and now again, don't take it out of the ice. Keep it in the ice, but just off the bottom. If you need to pick up enough to read it, pick up enough to read it, and record both of your temperatures. The question is, once the temperature bottomed out, but then the ice is still melting, does the temperature change it? No. Once it bottoms out, it stays there. We'll get to that in a minute. Okay, wait. You read it while it's in there, not after you get it out. Okay, have y'all recorded then? Thermometer 1, observed melting point. Thermometer 2, observed melting point. Okay. What's your measurement error? What should the melting point be? 0. If you're anything off from 0, that's your observed error. And it's either plus or minus. If you're below 0, it's a negative error. If you're above 0, it's a positive error. Did any of you have an error?
Yes.
I wouldn't be at all surprised. Was it very much?
1 degree.
1 degree. That's about normal. Okay? Everybody done that?
If it was 2 degrees, it would be plus 2 because it was above 0.
2 above 0? Yeah, that'd be a plus 2. So whatever you read, that was your measurement error. Because if you're minus 2, it's okay. Now, observed boiling point, you've got that one too, right? For both thermometers. And then the barometric pressure we already did, deviation from normal. Now, you got to do a little calculation here. Go back to your first page. Okay? We know that we're 4.54 millimeters of mercury above normal. So in the second paragraph there, it says, an atmospheric pressure change that increases the height of the column of mercury will increase the boiling point by 0.073 degrees Celsius per millimeter of mercury. So 0.37, that will be degrees Celsius for every 1 millimeter of mercury. Okay? So if you take that 0.037 and multiply it by your 4.54, not the 764, 4.54, your deviation. 4.54 times 0.0370. What do you get? 4.54 times 0.037. Say again? 0.7 what? 72?
0.17.
Well, 0.17. Okay. So, your accepted boiling point then would be 100.17. So it doesn't change it much. Can you read 0.17 on your thermometer? No. I don't think a single one of you can. I can't. So, but that is your accepted boiling point for both of them was 100.17 degrees Celsius. So what's your measurement error? Okay, you had 2 thermometers, and you should have gotten 2 temperatures, one for thermometer 1 and one for 2. Subtract, whichever the higher is from the lower, and your observed boiling point. Subtract from that the accepting boiling point, and that'll give you your measurement error of the boiling point. You understand what I said? Subtract. Put down your observed boiling point, whatever that was, for thermometer 1 and thermometer 2. Do them one at a time, and then subtract from that your accepted boiling point, which is 100.17. So it's not going to be much different, but see what it gives you. And that will be your measurement error in boiling water. Now, while y'all are doing that, I'm going to monkey around with something else. Okay. Have all of you filled out every block on your table?
Yes.
Okay. There's one other thing, or a couple other things we're going to do. First, we need to, okay, wait. Let's first go back. We have now done procedure. 1 on page 147. We've done 2 on 147. We've done 3 on 147. And we've done it for both thermometers. We're not doing separate trials, we're doing it for 2 thermometers. Okay? You can start working anytime you want to on the questions, results. Okay? There's question 1, 2, and 3 on page 149. There's question 4 and 5 on 150. Now, question 5 does need to be answered. I don't care what you put there, you put what you think. But if you leave it blank, you don't get credit. If you put an answer there, what it asked for, then you get some credit. Now, you can do that anytime, but what I want you to be doing right now is you determine your data from your best thermometer. You got 2 thermometers there. Which one had the better result, the least error? Okay? You decide that as a group. Which one has the least error? Okay? Now, okay, are you listening?
Yes.
From your best thermometer, not trial, best thermometer, this is on page 151, top of the page. Are you listening? Okay?
Yes.
Make a graph by plotting the temperature scale on the horizontal axis and the Celsius scale, temperature scale on the horizontal axis, and the Fahrenheit temperature on your vertical axis. Okay? Now, you have to determine what your Fahrenheit scale was, because you measured in Celsius, right? Do you remember the conversion? Now, does everybody have this up here?
Yes.
Okay, everybody got the barometric pressure and your change of temperature, right? So I'm going to erase that. I don't want to mess with any of theirs. It's their lab. I don't want to mess with them. I appreciate them letting us use it. So I'm going to try not to mess with it. Okay. Now I want one of you, or several of you if you can, to tell me what the formula is for converting Celsius to Fahrenheit. Okay. So what we're going to have, we're trying to get to Fahrenheit, so TF is equal to, and you do put the 9 over 5, 9 degrees Fahrenheit for every 5 degrees Celsius. You don't have to put the symbol in there, but I did. Times your degrees Celsius, temperature degrees Celsius. Okay? And once you've done that, you then add the 32 to it. Because that's degrees Fahrenheit too. Okay? So you do that for your melting point. Block number, they don't number them, but it's block number 1. So somewhere on the, whichever thermometer you chose as your best, thermometer 1 or thermometer 2, in that same block that you have your observed melting point, you put, that's in Celsius, you put the number you get from here when you do it in Fahrenheit. Okay? And before you do it, you might want to run it by me and let me see if it makes sense. Okay? Everybody following what I said? Use that formula there. You measured melting point in degrees Celsius, multiply that by 9/5, and then once you multiply that, add 32 to it, that gives you degrees Fahrenheit. What you got?
Listen, there's a question.
Okay. Okay. What that means is,
I mean, I seen a big blank below it, and I wasn't sure.
yeah. It definitely is something to fill in. It says account for any differences observed in the melting and boiling point readings, and you had 1 degree here, none there, and you had pretty high. Okay, so they're about the same. Now account for that. Why do you think you have some differences?
Elevation.
Not really, because that's taking
Barometric.
No, that's taking account because you took account. That's why you subtracted that off. Okay? What I would say is these are old thermometers. They've been used and abused, and they're probably fairly cheap. So I would say calibration error. Okay? They were probably poorly calibrated to begin with, or maybe gotten a little worse over time. Has everybody got degrees Fahrenheit for your melting point and your boiling point? On line number, observe boiling point. So observe melting point, the first one, and the one that you determine your best thermometer, okay, do its conversion to Fahrenheit, put that in the same block, you got plenty of room, and then observe boiling point, put that in the same block. Only convert from Celsius to Fahrenheit. And if you want to, run your numbers by me so you make sure they make sense. Okay? Got them? Now on your graph paper, I'm going to tell you how to set this up. Oh, there it is. Okay, it says put the Celsius temperature on the horizontal axis. So set it up what we call portrait mode, okay? Where the short side's on the bottom, the long side's going up. Put degrees Celsius on the bottom. Now you're going from basically somewhere from about 0 to 100. You have 1, 2, 3, 4, 5, 6, 7 big blocks. So if you need to, did any of you have any readings below 0? No, okay. So you can put 0 here, 20, 40, 60, 80, 100. So you use just the first 5 blocks. So some of you did have some readings above 100. So you have room for that. And then on the Fahrenheit scale, unfortunately, well, you have to do your calculation first, but then you've got 30, 50, 70, 90, 110, 130, 150, 170, 190, 210. What you might have to do is on the vertical scale, go by 30s. So 0, 30, 60, 90, 120, 150, 180, 210, and 240. Okay? You're not going to need anything as high as 240. Okay. Have you done your conversions? Got the Fahrenheit temperatures for both melting and freezing? Melting and boiling? Everybody?
No, not yet.
Anyone not done those yet? Okay. Are you having trouble with them or just do it? Back on the page. Which is your better thermometer? They're the same. Either one of them you want. Okay? So this will be, by the way, I can go. Yeah, that's what you did. Multiply by 9, divide by 5. Tell me what you get. Okay, has everyone got your melting point, degrees Fahrenheit, and your boiling point, degrees Fahrenheit? Okay? What's up here? Okay. And you're plotting them now?
Yes.
Okay, did you go to 30?
I did these like 25.
Okay. Not bad. Yeah, that's great. Actually, 25 does work pretty well. That's all of that. Yeah. Degrees Celsius times 9/5. Y'all get tensions already?
We're just
Good. Now you graph, and actually the team up here came up with, I said 30s. Actually, your Fahrenheit scale, the vertical scale, you can actually do by 25, and it comes out even better. So you don't have to. Each block is 25 degrees. Okay? Draw your 2 points and then connect the line in between. Now, you only need one. Which one are you going to stress? Okay, so it makes it better for mine. That, okay? Perfect. That's the best. Okay, that's the one required. Yes. Fahrenheit. Exactly like that. That's fine. This is going to make it look good.
Oh, surface area.
Okay.
Jumped up by what? It is all about how like 6.
What's that?
I was
Oh, okay.
discussing.
All right. I didn't know this was going to take so long. Okay. All right. Have you drawn your graphs? You've done your calculation. You got degrees Fahrenheit. Then you drew your graphs. Have you calculated your slope yet? Okay. Now remember what slope is? Rise over run. And your rise is simply the difference of your Fahrenheit degree divided by your difference of your Celsius degree. Rise over run. So you've got the numbers there, just do the calculation. Has everyone calculated the value of your slope? Has everyone calculated the value of your slope?
Yes.
Okay. Now, can you answer the next question? Oh, you haven't? I'll help if you need it. You got it? Okay. Now, if everybody's got the slope, value of the slope, what's the meaning of the slope? What does that mean for you? Someone give me a few of the values you have. Say again? I can't hear you. What's the value of your slope?
She's got a 2 degrees Celsius. Okay. Calculate degrees Fahrenheit, 100 degrees Celsius, you write them here, here, somewhere here, somewhere here.
Yeah.
Everybody got it slow?
Sure.
You know how when you first one is like all the way completely, that's been halfway swap with the green.
Okay. Has everybody got or working on getting a slope?
Yes.
Okay. Now, on your graph, have you, okay, wait, now, before. Okay, so you wrote down under, on page 151, number 1, the value of the slope. You wrote it down, right?
Yes.
Okay. Did you also join any group you want to? All groups have 3 people, you'll be the 4th. Okay. What is the meaning of that slope? How did you get it? Say again? Relationship? Is that what you said? Yeah, absolutely. It's the ratio of the change of Fahrenheit over change of Celsius, right? That's exactly right. The meaning of the slope is the ratio of the change of Fahrenheit to change of Celsius.
Y2 minus Y1 over X2 minus X1.
That's exactly it.
Well, we have the same, that's going to be 0, isn't it? 0 on the bottom. You have to do, what, 35.6?
Wait. Pick your best try. You said it didn't matter.
It didn't matter. So
Okay, so just pick one try.
So try 1.
Try 1. Okay, here's your Y2. There's your Y1. There's your X2. There's your X1. Nothing is good.
So it should be X. Should be X2.
Yeah, your horizontal is your X.
Okay.
I would say X1.
Okay.
This is X2.
Okay.
There's your Y2. There's your Y1.
Oh, okay.
Your Fahrenheit's on the vertical scale. Your Celsius on the horizontal scale. Okay, so everybody got the meaning of the slope. Okay. Now, what's the value of your y-intercept? Okay, we got 32. All right, now, might be helpful to listen up. Okay? Okay. Number 3 on page 151. The slope-intercept form for an equation of a line. Okay, has everybody got your temperature scale formula done? Okay, I can erase this? Okay. All right. Now, question 3 on page 151. The slope-intercept form for a line is, you should know this, y is equal to mx plus b. Right? You recognize that from your math classes, right? Now here, your y is the variable on the y-axis. What was your variable on the y-axis? Now your variable. It's not a number. Your variable. Fahrenheit. Degrees Fahrenheit. Exactly. As it says on your book. There's your thing here. The x variable was the degree Celsius. Okay? Your M was your slope. You said you calculated it in number 1, right? Okay, so that's the calculation for number 1. Okay? And B, y-intercept. You told me you wrote that down on number 2. So what you do then, use this information to write the equation of the this temperature graph you just did. You told me the y was degrees Fahrenheit, right? Is equal to whatever number you got there for your slope times degrees Celsius plus 32, did you say, or whatever yours happened to be. Okay? That is what it is. Okay? What's the meaning of that equation? What's that again? Absolutely. You got it. Because what was your slope here? Someone give me your slope. Second?
4/3.
Really?
9/5. Yeah.
Okay, did you actually get 9/5?
It was close to.
Okay. What do you get when you divide 9 by 5?
1.8.
Exactly. And what was your slope? If you did it as a decimal number? When you divide the rise over the run, what did you get? What's that?
Sorry, bud.
1.82. And it's awfully close to 1.8. So yes, what you just did was derive your Fahrenheit, Celsius to Fahrenheit conversion. That's exactly what you did. So that's the meaning of the equation. Okay? Now we're going to do one more thing before you leave the lab today. Okay? And I'm going to do it, but I want everybody to come see it. So when you're through writing, come up here to see this. Yeah, you get to drink it. Whoever can drink it first. No. One person drinks from the Dr. Pepper can, one drinks from that, and one from another.
It's 35.
Okay. And let me remind you also, don't forget to do your results section. Remember, questions on page 149 and 150, questions 1, 2, 3, 4, and 5. Okay, I already said that, but I just wanted to remind you. Well, some people maybe not have been here when I said it. Okay, when you're ready, we'll come up here. You see steam coming down. Okay. All right. Okay, you can work on answering your questions later if you want to, but I want you to see this part. And what this part is on invitation to inquiry on page 151 at the bottom of the page. It says wash an aluminum pot can, Dr. Pepper can. I did that before class. In fact, I did it several days ago. But I've left a small amount of water in there. I put it on the heat, and you can see it steaming, right? Okay? Now, what I'm going to do is pick up that hot can and invert it into this ice water. Anyone want to make a guess? It's going to shrink, you say? Okay, y'all ready to watch? I see one team back there that's not up here. Huh? I think if it was going to melt, it would already be melted. Okay? Oh, you say the ice is going to melt. Okay, that may be true. Let's see. Has everybody got so they can see? Okay? This is hot. That's why I'm turning it up. Okay. What happened? Okay, you said it shrunk. It was a little bit more than shrinking. Okay. Now, any idea why that happened?
Because it was so
Pretty
hot
major
inside,
shrink,
it didn't come in.
What's that?
It was so hot on the inside, it made the water
Okay? I think you're right on to something there. Okay? Now, we didn't go over Charles' law, Boyle's law, molecular point of view, but let's talk about it a little bit. Okay? What we had here was in the can was a small amount of very hot water and then a lot of steam. You can see the steam coming out, right? Over there we had ice water. We inverted it. What happened inside? Number one, that a little amount of hot water didn't matter too much, but that steam that was vapor, it cooled really quickly, becoming what? Water. Condensing back to water. Well, what takes more volume? Yeah, steam or water? Steam takes a lot more volume. So what happened then, you condensed the steam into water, the volume shrunk like crazy, which reduced the pressure that was in the can. And what was the pressure outside the can? Atmospheric pressure. Did you know that the atmosphere did that to it? Exactly what it was. You lowered the pressure inside the can, and the pressure outside was still right around atmospheric pressure. Yeah, you tilted a little bit into it, but I just barely got the top in there. It was atmospheric pressure pushing in on it. There's a lot of pressure on those folks. I'm not talking about school. Okay? A lot of force acting on that. Okay. So you do your best to do number one. Answer that however you can. Under invitation to inquiry, at the bottom of page 151, number one. Don't worry about 2 and 3. We didn't do anything that would do that. Okay? And please don't forget to do your results. And don't, okay, you finished everything? Okay? And also, I want to suggest to you, be sure you turn in to me on the front table here your thermometers and your rulers.
You said I do 23 on this one.
Do all the answers. Say again? Which one were you talking about?
No, I'm talking about, you said something about 23.
Okay, wait. Okay, when you're through with the lab, you should have 3 answers on page 149, 1, 2, and 3.
Oh, all right.
2 on 150, 4 and 5. You should have 2 answers under 1 on page 151, 1 on number 2, and you really should have 2 answers on 3. It says, write that down and then give the meaning of it. And then invitation to inquiry on 151, number 1, you should have that answer, but 2 and 3 you don't. Okay, I see what you're talking about. And then on page 152, you should have a filled out table for both thermometers, and you should have some Fahrenheit temperatures for your best thermometer, and then you should have a good graph. And if you make your points big enough, you can get a straight line to go through anything, right? Okay. Never mind. Okay. Oh, your test. Okay. Did I get anything of yours wet?
Oh, no, sir. I appreciate it. I get the other back.
Okay, the last test we did. Oh, yeah. While y'all are finishing up here, I got to run down to my office and get something for Shanika. I'll be right back. I'm going to turn off the recorder if it's okay.